Hi, this is Scott. I really appreciate our sponsors because they make the show possible. Today's show is sponsored by Developer Express. Become a UI superhero with Dev Express controls and libraries. Deliver elegant .NET solutions that address customer needs today. By leveraging your existing knowledge, you can build next-generation touch-enabled solutions for tomorrow. You can download your free 30-day trial at dx.hanselminutes.com. That's dx.hanselminutes.com.
From hanselminutes.com, it's Hansel Minutes, a weekly discussion with web developer and technologist Scott Hanselman. This is Lawrence Ryan announcing show number 472. In this episode, Scott talks with Aaron Stannard about the Akka.NET open source project and the actor model.
Hi, this is Scott Hanselman. This is another episode of Hansel Minutes, and I am chatting today with Aaron Stannard, who works on a project called Akka.NET. How are you?
Hi, Scott. Good to see you.
Yeah, thanks for doing this. I appreciate it. We hung out a little bit at .NET Fringe, which was a very fine conference here in Portland.
Yes, it was. It was a lot of fun. We gave, like 7 hours of the workshops on Akka.NET on Sunday, and then had a talk on Monday, and then a little lightning talk on Tuesday.
Yeah, you did more than just a presentation. You did a whole day of workshops, just breaking it down.
Yeah, I thought I was going to die by the time I was done speaking for like 7 hours straight or whatever it was, plus all the questions I got asked afterwards. But it was really fun. We got to train, I think, 50 people on Akka.NET in one sitting, so that was cool.
Have you ever done training like that before?
I used to work as an evangelist at Microsoft.
Oh, you did?
And I did. I worked on the field team in the United States for startups in Southern California. And so I started this series of Node.js on Azure boot camps. This would have been like really late 2011, early 2012. And I've done that before, which is sort of an all-day format. But usually I had more people to sort of help and everything else. And the content was kind of, I'd say there's a little bit, there was a lot less new concepts to cover in that stuff.
Yeah.
Everyone was already pretty familiar with JavaScript and how web servers work.
Yeah. I've actually I used to do full-time training, like three weeks a month, 40 hours a week, 8 hours a day, standing up in front of people. And this was like teaching people classic ASP. So you had to teach them, like, here's a request. Like, whoa, slow down. So you had to introduce people to Akka.NET. So what is Akka.NET? Introduce it to me.
Sure. So Akka.NET is a port of a project called Akka that was invented for the JVM. And it was written in Scala and Java. And what Akka is an implementation of the actor model. The actor model is a very old concurrent programming technique stemming back from like 1973 is when I think it was invented. And the first real commercial implementation of it that we all sort of know and recognize today was the Erlang and OTP programming language. So if you read the case study about WhatsApp and how they're able to have, 12 engineers basically manage their entire infrastructure for doing 500 million messages a day or whatever it was. They're a really good Erlang success story. TypeSafe, this company behind the Akka framework, wanted to bring that same sort of concurrent programming model to the JVM. And so they were really successful in doing that. And then Akka kind of evolved into being a really powerful distributed programming framework from there. One of the properties of the actor model that makes that possible is this notion of location transparency. So what the actor model really is essentially, in object-oriented programming, everything's an object, right? In the actor model, everything's either an actor or a message. So actors represent these little classes that effectively act as like microprocesses. They can be restarted, they can be started on a remote machine, etc. And the way actors communicate with each other is via message passing. And one of the things that makes it really powerful is that, one, message passing is inherently asynchronous. Actors run on their own thread. You can have 1 million actors share a small thread pool. And the other thing that's really special about it is that if an actor wants to communicate with another actor on a remote machine, that detail is transparent to you as the programmer. sending a message to a local actor versus an actor running on a machine in a remote data center 1,000 miles away is a implementation detail that you don't have to think about when you're sending a message. It's something that the location transparency built into the programming model sort of takes care of for you.
Mm-hmm. Okay, so there's a lot of concepts there. So let's tease them apart a little bit because I've got a lot of questions. So first, I remember being around in the mid-90s. Gosh, is that 20 years ago? Basically when we were doing things like COM, right, the component object model, and then DCOM, and it was talked about that location transparency was an implementation detail. I may have actually been on stage at some point and said those words. And there were things about DCOM that really worked, but then there was also kind of an oscillation in the industry where we switched to the opposite side and said, wow, we really should recognize that latency is a thing. And web services then went the opposite direction. Not only were they high latency, but we also kind of explicitly said that out of process cross system calls cost. How do you reconcile those two things?
So that's a great question. And one of the things that's different between sort of DCOM and COM and the actor model is that the actor model is asynchronous by default, right? So when I send a message to an actor, even one on my local process, it might not respond to my message immediately. It might have a queue of a million other messages in front of it has to work through, and there might be some delay in it responding to me. And that's just on a local process. Well, if you think about what the delay might look like over the network, particularly when there's latency involved and all sorts of other stuff if you're traveling over the open internet, that latency just becomes something you account for in the design of your actor system. So you can use techniques like, for instance, the ask method inside the actor model, where you say, I expect this response back from this actor within this real-time constraint. And if I don't get a response back, we're going to time out and then do something else. So that's sort of built into your thinking and modeling about the problem. There's that latency is just a side effect of asynchronicity to begin with.
Okay, so then if I can paraphrase to make sure that I understood, with COM and DCOM, it was more of a remote procedure call kind of a thing, where we're going to take this object that has methods on it and remote it, and then, pretend that it's not really remote, and then feel bad when it's slow. And you're saying in a message passing model, you're expecting that this isn't an instantaneous thing that's going to happen. It's hey, go ahead and do this, queue this up, put this order in a cart or whatever. And because your system is asynchronous, presumably all the way back up into the UI.
Yep.
Then it's a much different model.
Yeah, exactly. So actors get dispatched asynchronously. So actors by default are extremely lazy. We have this image on one of our blog posts where we introduce the concept of actors, where it's literally a mailman sleeping inside a mailbox. That's sort of the right model for thinking about what actors do. If they aren't receiving messages, they're just hanging out, not really doing anything. But when a message arrives in an actor's mailbox, the actor then gets dispatched, handles it, and then goes back to sleep or waits for another message to come to it. So the idea is that, actors are all sort of message passing is done asynchronously all the time, regardless of the scope of how the actors are deployed.
Okay, so then when I was doing this stuff, a long time ago, we had sockets on ports, and then we had queues. What kinds of things can actors communicate over?
So right now, by default, actors communicate over sockets. So it's all done over TCP or UDP, and you have the ability to go and write other custom transports if you wanted to. So for instance, if you really wanted to use a named pipe or something like that, you could use that to communicate between actors. Other models that we do see, though, from customers who are usually trying to, when I say customers, I'm referring to my company, Petabridge. We provide commercial support for Akka.net. But what we see them do oftentimes is they might have a pre-existing system that has something like N-Service Bus or RabbitMQ sitting behind their web front end. And they want to use Akka.net to more efficiently handle the processing of those published messages in that queue. So a lot of times what you'll see people do is write a system that has an Akka cluster consume messages off of an existing message queue. We don't really recommend that for communicating between actors because that's so heavy compared to the built-in actor message queue and network transport stuff that Akka.net already gives you. But that's that's one model we do see for people who are transitioning off of some older system onto an actor-based one.
So as someone who spent a lot of time building distributed systems where we wanted to be able to choose our transports, how worried should I be when I hear that I'm buying into a model that is not only an architectural model, but also presumably an unknown implementation of some kind of sockets thing that I've never heard of? Like, I was thinking, oh, this is a cool abstraction, and now I'm thinking, oh wow, I have to worry about sockets. Should I worry about that, or should I just let it go?
Well, you shouldn't worry about that. What Akka.NET gives you is there's a built-in addressing system. Every actor has its own unique URI. And so that detail, by the way, is usually abstracted away from you. The actor reference, which is how actors communicate in both Akka and Akka.NET, it's like a handle to an actor. You don't send a message directly to an actor instance. You send a message to its handle, and that handle is responsible for putting a message into an actor's mailbox. Then the mailbox is responsible for sort of activating the actor. So there's sort of a decoupling of the different pieces of the messaging infrastructure there. Transports like TCP connections that Akka.NET manages will be opened for you automatically when you need to send a message to a remote address. The Akka cluster module, which is an abstraction that we have, an even bigger abstraction that we have sitting on top of our remoting capabilities, will abstract away a lot of the addressing and socket management stuff for you to a point where all you have to do is connect to one node that is at a well-known IP address, and then from there, every individual Akka.NET process will be able to essentially form a connection to any other node in your network. And that's sort of handled for you auto-magically.
Is that one node have all knowledge? Is that a single point of failure?
No, that one node, you can actually have more than one node, more than one well-known node to communicate with. You just need to have at least one.
I see.
So this is a clustering strategy that Cassandra and Riak and a couple of other big distributed database technologies use. It's called a seed node, is the idea. Yeah. So you seed the cluster with one or more nodes at a well-known address, and that's your sort of entrance point of discovering all the other ones that have joined.
And then as nodes come and go, do they all let each other know and they all vote about what's going on in the current state of the system?
Yeah, exactly. They use a gossip protocol to sort of say, hey, I can't connect, node A can't connect to node C anymore, node B can't connect to it either. Okay, then the leader will go ahead and say, all right, well, node B's dead. We got to just, go ahead and remove it from our routing tables and everything else.
I in my mind, when you just said that gossip protocol, I have this image in my mind of like people texting like, I haven't seen Frank in a week. Yeah,
is he all right? Is he okay?
I don't think so. I don't think he made it out of the club.
He took it really hard last night, Just
okay, so and if I want to talk to an actor, I talk to a reference to an actor. That goes over a transport that I shouldn't worry about. And goes into the actor's mailbox, which is an internal queue, or is it being held in memory?
It's being held in memory. It's essentially what it is just a set of synchronized queues with different channels. Okay. So there's some messages that get prioritized ahead of others. So system messages that are built into Akka.NET, which include things like, hey, you need to restart because you're in some faulted state. That sort of stuff is a system message.
Do I have to... is that durable? Do I worry about the mailbox being in memory?
So we don't have to worry about the mailbox being in memory, so to speak. What we do need to do, though, is for scenarios where you have messages where you need to have guaranteed delivery. By default, Akka's message delivery guarantee is best effort, which means at most once. And so that's
a pretty minimal effort, wouldn't you say?
It's best, kind of ironically named, right? Best effort means
that's like the UPS guy where it's like, I'm going to do my best. I will ring your doorbell once.
I'll ring your doorbell once. I'll leave the package down. So that's what's built into Akka by default.
Okay.
What you can do, so the way Akka works is, think of it like Home Depot. You have additional modules that provide new sets of tools and parts for you to use to build a system. We have one module called Akka.persistence. And this is a way of setting up two things. One, actors that have durable internal state, where they basically are able to take messages and event source them to something like Cassandra or a SQL Server or Azure Table Storage. And if that actor dies, let's say the entire process crashes, like a machine went down in your Azure cluster, and it comes back, then it's able to go and rehydrate its state from internal source. We have a special built-in actor called a guaranteed delivery actor. that is able to maintain a buffer of messages that need to be sent over a wire to another remote system. And it expects an acknowledgement back that that message has not only been received, but it's also been processed by the other end of that connection. And at that point, it basically dequeues the message, and you don't have to worry about it being persisted anymore because it's been handled.
You mentioned that I might use Cassandra, but isn't Cassandra another distributed system that's not written in .NET? Why would I want to have two distributed systems talking to each other?
Basically all it is that the Akka persistence module has a pluggable layer to work with whatever data store you're already using.
I see. So I could introduce Akka to an environment where I'm already having some success with Cassandra.
Yeah, exactly. So, and when I used Akka.NET in production, I was already using Cassandra. And so I used that as my sort of backup for messages that needed to have some durability. Mm-hmm. But we have a pull request out there for a SQL Server module, and I think we have a contributor who wrote a get event store plugin for Akka.persistence too.
Yeah. I was thinking what this would look like with Service Bus.
Yeah, Service Bus would be another one potentially. I think I've seen some people want to do integrations. This wouldn't necessarily be an Akka.persistence implementation, but Azure Event Hubs has been something that people have been real interested in.
Yeah.
So
okay, all right. So actor reference over a transport to a mailbox. Mailbox is an internal queue, and then actors, I assume, have some behavior that they want to do based on whether or not that mailbox message is actionable.
Yeah, exactly. So when you're writing your actor code, the only method you really need to fill in by default is what's called the onReceive method. And it just takes a plain old object as its sort of property. And that object is your message. And so you have to do a little bit of, I guess, pattern matching is sort of the functional programming name for doing this, where you inspect the message by its type. Is this message a string? Is this message
How does that not turn into a switch
class?
statement? How does my magical distributed system not turn into a switch statement of like, are you a string? Are you an object?
Are you a string?
Do I deserialize you?
So, well, the serialization is handled for you transparently.
Oh, okay.
So that's
cool.
One of the things that's really nice is that we have a serialization system that makes it so if you're passing a message to another actor in memory, that's all handled via in-memory queue. So there's no network transport there. Okay. Over a remote system, we sort of abstract the detail of it being serialized and just make sure that on either end of the connection, you don't have to worry about it. So we use a combination of Google protocol buffers and binary JSON for that.
Nice. Both very fast, very tight protocols.
Yep. And when you get a message back, we have a couple of tools you can use in C# for doing pattern matching. We have an F# API too, and you can use the built-in pattern matching that the language supports right out of the box there. But in C# we have two tools for you. One is we have a special type of actor called a receive actor that allows you to define lambdas and predicates for doing pattern matching that are strongly typed.
Nice.
And they're also very fast, by the way. So they get sort of compiled and cached. And you're able to do things like, is this message a string, and does the string start with blah, effectively? And that's the sort of stuff that we're able to sort of make easy for C# developers.
If I'm doing a distributed system, and I used to work in, I don't know if I told you about this, but I used to work in banking, retail banking. So I worked on a large DCOM-based distributed system that ran on a number of large banks. And we struggled with the identity, the object identity. Like, we like strong types, but at the same time, this object is going to be an account, and I'm going to send it over to this other machine, and it needs to think about an account. Am I using an interface? Are we sharing a DLL? Are we just putting it in a hash table? The object identity as it relates to serialization has been a challenge historically. How do you deal with that?
What we do right now is for a distributed system where, let's say you have multiple Akka.NET sort of services that have formed a cluster together. Mm-hmm. The way we have people work with that problem today is making sure you have a shared assembly that defines all those common message definitions that are going to be passed over the network. So that way, when JSON.NET deserializes your network request back into a POCO object, it has a common definition on both ends of the wire. Mm-hmm. We're playing around with some ideas now for being able to do that dynamically without needing to deploy an assembly at runtime, because one issue that comes up is the notion of versioned messages, right? What if I need to make an update to this message that's a big part of my domain? How do I deal with that?
This was a huge problem for us 15 years ago because we might want to change a message, but there's certain parts of the system that are, let's just say IT is less likely to let us drop in a new DLL.
Yep. They're not likely to let you drop in a DLL where you have, the payment gateway or whatever sitting right there.
So we ended up just doing hash tables.
Yeah. So one of the things that a couple of patterns that I've seen our users use for dealing with this. One is just the tolerant reader pattern, where you basically are able to, while a system's in a state where some of it's updated and some of it's not, the older clients can still read the parts of the newer messages without throwing an exception or failing. So that's one idea. That's a Martin Fowler pattern, tolerant reader. And I personally have used that, and it's been successful. The other thing I've seen people do is actually version. When they have to do a major change, you shouldn't be changing your message types all the time, right?
Sure, of course. Usually, if you're lucky, it's additive.
Yeah, it's additive, right? So when people need to make a major change, I've also seen them use namespacing in their assemblies, right? Well, they'll go ahead and have a separate namespace for V1, V2, V3, and I've personally done that before too. So those are not as elegant as something that can, hot load an assembly definition, or maybe have your own form of dynamic sort of serialization.
Some kind of duck typing, or some kind of like what used to be called assembly neutral interfaces, where if it lines up, right, if you have an object, regardless of identity from a .NET perspective, if I got a person object and it's got a first name and a last name and they both got strings, your person and my person are equivalent. So I could have my own implementation of a person, and you could have your own implementation of a person. They could even have different implementations as long as their public properties line up.
Yeah, exactly. And that's essentially the tolerant reader in a nutshell.
Oh, awesome.
Yeah.
Too bad I didn't come up with the idea and take credit for it.
You could have had a Martin Fowler blog post. Yeah, take that.
Okay. So the behaviors then that an actor does, if I'm an actor that gets a message and I want to write to a database, do I just write to the database, or do I tell another actor, like a child actor, to do that for me?
So that's a great question. So one of the benefits of using actors is reliability. And there's a lot of design patterns around it. And so Erlang's philosophy, when they first really implemented it, was that it is cheaper just to try something and let the actor fail or die than it is to do try, catch, restart and all this other sort of stuff that we would normally do in everyday procedural programming. But one of the things we need to do to make sure that's done reliably is use some patterns that delegate dangerous work, like network calls or parsing or writing to the file system, to actors that are purpose-built for doing that. So if you have
character actors.
What do you say?
Character actors.
Huh?
You know what I mean? I don't know who we can get to do this reliably. I think John Malkovich is available. Oh, he'll be perfect. Now we don't have to worry about that job. Huh? I just invented that, by the way. Suck it, Fowler.
The character actor
I'm going to write an article
pattern
called The Character Actor. That's purpose-built actors, my friend.
There you go. Purpose-built actors right there. One of the things that took me, I'm embarrassed it took me this long to figure this out. So in Akka, you use props to create an actor. Props is like a formula for basically how you build an actor. And it took me like a year to realize, because actors need props in order to act. Yeah, I was like, man,
This is what's so fun about object-oriented programming and patterns and stuff like that, is that when the analogies are good, like the ones that you're using, they resonate. And it really helps you understand the system. I mean, in this case here, this all works for me.
Yep.
Okay. So you said purpose-built actors, character actors. We'll go and do that specific kind of work. And they're reusable, I assume. They're generic.
Yeah, absolutely. And they can be deployed anywhere in sort of the actor hierarchy. Actors are organized in like a family tree. So Akka gives you this sort of like little root actor at the very top of the stack. Mm-hmm. And then every time you go and create, what's called a top level actor,
your headliner.
A headliner. There we go. We're getting really good with the figurative language here.
Yeah, I'm ready to go. I'm going to write whole papers on this.
So you have your headliner. Then you might have some supporting actors that the headliner creates. And then after that, you've got your character actors. And then you might have some stunt doubles after that, right?
Ooh.
Yeah.
Okay, that makes sense. So there really is a family tree, and they're actually talking to each other? And there's ownership issues, right? Like if what happens if the parent dies? Does everyone else underneath them go away too?
Oh, yeah. So if the parent dies, that whole rest of the actor hierarchy gets wiped out.
Okay.
So one of the things that's built into actors, though, is the concept of parental supervision. Parents supervise their children. Mm-hmm. So if a child fails, let's go ahead and say that customer actor we had before goes and creates a child actor. We'll call it's a database actor.
Sure.
For writing to the database, and that actor fails. Let's say, your connection to SQL Server gets lost or something. The parent actor will go ahead and get the exception that actor threw back as a message, and it'll make a decision about what to do. How should it reconcile the fate of that actor? So it has three choices it can make. One is it can tell the actor to restart, which is the default sort of choice. Okay, we're going to go ahead and reboot this actor back to its clean state. So all the internal state in that child will be wiped out, and it'll go ahead and use the props that we created to go back to an initial clean state.
Okay, take 2.
Take 2, exactly. And we'll do up to, by default, we'll do up to take 10 within some period of time. And then we'll decide, okay, this actor is permanently screwed.
You'll never work in this town again, son.
Exactly, and we'll just kill it.
Okay.
And then the last thing that a actor can do as part of its supervision strategy is say, I can't figure this out. I'm going to escalate to my parent and see what's going on.
Call their agent.
Yeah, call their agent, exactly. Or call the producer.
Now,
or whatever.
Interesting. So this makes me think about it in the terms of exception handling. I'm used to it being scoping at the language level, but this is exception handling scoped as a tree of objects. And rather than the exception throwing up outside of a call stack, it's throwing up and going up within this tree of actors.
Mm-hmm.
Okay, and then you're monitoring all of that. Like the larger orchestration framework is aware of what's going on.
So it's kind of cool. It's actually pretty decentralized. So the central Akka.NET actors have no idea, like the system actors that are responsible for addressing and all the plumbing and that stuff.
Mm-hmm.
They have no idea about failures happening way out on the edge of the family tree. If great cousin Jimmy or whatever has something goes wrong with them, the top actor at the top of the hierarchy has no idea.
And it does because it doesn't destabilize the entire system. Exactly.
So failures are local, essentially, until they're not, right? If you have some cascading failure that goes all the way up, then at that point, the entire actor family tree might reboot.
Right. You've got an extra, he's being a dork, but it's in the background of the camera, you don't worry about it. But the guy knocks Brad Pitt over, then we have a problem.
Yes, exactly.
Can the system recover if something really bad happens?
Yes, it can. The systems are designed. One of the benefits of actor systems is that they are self-healing. So they're able to recover from failures. And what might happen is in the worst case scenario, let's say, like just short of the process crashing and having to be restarted, let's say you have an exception that kills off all of your top level actors and they all need to be restarted. So it'd be something really bad, like usually it's some network resource that application absolutely depends on failing that would cause that. What can happen is your application will reboot to its initial state and start building itself back up again. And if you're using capabilities like Akka.persistence, where some of that data is backed up to a database, it can recover its state on its way back down.
Why would it be preferable for the Akka system to reboot, quote unquote reboot, rather than just rebooting the machine or the Docker container or the Windows, or the at what point is a reboot really a reboot, and when should you just freshen the whole thing?
Well, the reboot of the actors is done solely through your software, right? It requires no human supervision. Making the choice to reboot a machine, you can program that, of course, using some plugins of the Azure SDK or something else like that to go and automatically do it. Mm-hmm. Or you can use like process monitoring tools to go and do that.
Right.
But typically the idea behind the actor model is that every single little microprocess, every individual actor can be rebooted independently if needed. So
and
that's
is
just
it okay to do that though? Like I used to work on systems where they had memory leaks, and rather than dealing with them, they would just say, "Oh, we'll just recycle this, every 20 minutes." So they built in abuse of rebooting as a part of the system because they found it was such a great feature. Do I want my actors restarting all the time?
No, you don't want your actors restarting all the time because that means your application, like actors only restart when you throw an exception. Okay. So that means you're doing something bad if your actors are restarting a lot. What you do want though is actors are cheap, disposable resources. You can go ahead and create a big hierarchy of actors for some job, and then you send the top actor of that hierarchy a poison pill, and it basically goes and kills off that entire part of the tree. Mm-hmm. That's totally fine, doing that sort of stuff all the time. Actors are cheap. You can fit 2.6 million of them in 1 gig of RAM or something like that.
Okay.
So, going back to our little Hollywood analogy here, most of them work as waiters during the daytime anyway, right?
Exactly. I'm an actor. Oh, really? What restaurant do you work at? So this is a port of Akka for the JVM. Do you no longer have a relationship with them, or do you all hang out together? How does that work when you port something to another language?
So we actually at first they kind of left us to our own devices. Me and Roger, the two founders of the Akka.NET project, both kind of were doing this for our own independent reasons, teamed up together. And after the project started to make some steam in terms of actually implementing real features and everything else, we reached out to TypeSafe and asked if we could call the framework Akka.net. Mm-hmm. And their CTO, Jonas, the original author of Akka, was like, yeah, sure, why not?
He's thinking, oh, that's adorable.
Yeah, exactly.
Yes,
oh,
these
that's
two
adorable.
random people. Okay, yeah, good luck with that, son.
But then, I guess about a couple of months ago, as the project started to get really big and we started getting a lot more traction and we had, hundreds of users and people tweeting about it, and then my company Petabridge started, then Roland Kuhn, the chief architect of Akka, reached out and said, hey, we should probably work together to make sure you guys are learn all the same lessons we learned the hard way and everything else.
That's very nice.
Yeah. So we have a partnership with them, and Roland actually is there we have a Gitter chat. It's like IRC for GitHub, basically. Roland's there and he answers questions from time to time. I've seen him active over the past few days. And me and the other contributors, we've even reported bugs in Akka that we found when porting things to Akka.net. So we have pretty open communication with their team. And the thing that we're really trying to achieve with a port is, one, we want to make it idiomatic C# and F#, right? We don't want people to deal with weird constructs that feel like they're leftovers from the JVM. But at the same time, we also want to preserve the knowledge that the Akka team accrued through years of super heavy production use. Akka powers parts of Walmart, Amazon, Cloud, Blizzard, and every single deployment of Apache Spark uses Akka under the hood. So there's a lot of really heavy usage of their framework. And so we want to, a lot of the problems that come up are really subtle things that they only found out because some customer of theirs ran into it,
Now, I think I know the answer to this because I did it for years, and I don't mean to sound like a shill, but do you think .NET can handle big distributed systems like this?
Absolutely. I've built one, on top of Akka.net, Cassandra, and ASP.NET. It totally can. What .NET's lacked for a long time in the distributed system space, I really feel like has been, one, a culture and an attitude of we can do this. I think there's been a lot of .NET developers have maybe had a feeling of not being good enough to really take on these problems. And I think that's BS.
Yeah, there's an inferiority complex.
An inferiority complex, there you go. So I think that's BS, and I think people are starting to change their minds about that now, too. The second part of it is I think we've really lacked a good set of tools for doing big data for a long time. I think that a lot of the innovation there really came from Python and JVM sort of worlds. But in .NET land, we're starting to see a lot more of it. Some of the other stuff they showed off at .NET Fringe, for instance, like Lena's talk on Embrace, is another really good example of a powerful distributed programming framework that's available exclusively in .NET. So I really think that .NET does have a future in big data. I don't think that you're gonna see something like Hadoop.NET anytime soon. But I do think for a lot of the problems that everyday .NET developers face, having frameworks like Akka.NET, Embrace, Orleans, and others available as tools to do it will help improve the state of our art to a point where this sort of distributed systems programming is pretty common in .NET. And I think that will happen over the next couple of years.
Yeah, absolutely. And I think also it's on us as people who've been in the community for a number of years to let folks know about this. I'm finding that the number one thing I see in the .NET community is that just people don't know about other really awesome open source projects. So I appreciate you, bringing Akka.NET to us and to me and sharing with me today on the show.
Well, thank you very much, Scott. I really appreciate the opportunity to help spread the word about Akka.NET. And if we can help empower .NET developers out there to take on challenges they didn't feel like they could do before, then that's a huge win for me in my book.
Very cool. You can check out Akka.NET at Akka.net. Great documentation, great getting started. You'll have something interesting running within 15 minutes. Thanks so much, Aaron Stannard, for chatting with me today. This has been another episode of Hansel Minutes, and we'll see you again next week.